In this video, I will explain how we can code a 2D model for heat conduction in a heat bed for a printer. So if we start by looking at the problem, we have a heat bed which has dimensions of 20 centimeters times 20 centimeters and a thickness of 0.3 centimeters. And if you look on it from the top, I have drawn it here, and we have an X dimension and a Y dimension. We also have the Z dimension, which is 0.3, but because we were told in the exercise that this is a 2D problem, we are right to assume that we can ignore any variation across the thickness of this plate. So we ignore the Z dimension. If we look at our governing equation for the rectangular coordinates, because that is what we will use here, we see the energy balance as it is here, and we have the terms here, which are all related to advection. Remember that advection is the movement of bulk heat, and since we are having a solid uh, aluminum plate here, there is no movement of the bulk aluminum in here. That would only be the case if this aluminum would be melted and fluid, and some force pushed this fluid aluminum around. Then we would have some advection, but that is not the case. So we can actually cross out all these terms where we have a V in front of it. So another way you would always be able to recognize this is if there is no velocity or flow rate described in the assignment, you can cross out these terms with advection. Then we are left with conduction, which is described over here, and a source term here. So we just decided that we had no variation along the Z dimension, so we can cross that out here. Then we are left with two dimensions where we have heat conduction, and we have the source term, which can be a source that removes heat or generates heat here. Since in the assignment we are told that we are losing heat from the surface, this S term here would actually be equivalent to the heat loss from that surface. So it would be in total a negative quantity going in here on the S space. And because we are interested in the temperature, not the energy flow, we divide by rho times Cp on both sides to get the final governing equation. We are also told that the temperature on the edges of the plate is 100 degrees. And if it's always 100 degrees, that means that we have a fixed state variable. And a fixed state variable at some boundary is the Dirichlet boundary condition. And because we have two dimensions and we have two boundaries for each dimension, we have four boundaries in total, which I have written here, and they are all equal to 100. So let's go to Python and see how we can code this. The first thing we do in Python is that we define the dimensions of the plate, which is 0.2 meters in the X and the Y dimension. We can also write what the depth is for now, because we will use it for something else when we have to calculate the heat loss. Then we need to pick some step size in both dimensions. So that could be, for instance, 0.005, and the same for dy. Let's just say it's the same as dx here. Because we have two dimensions, we need to make a spatial grid for both dimensions. We call it the X grid and the Y grid. And like for the 1D problems, we define the grids with the NP arrange. Like this. So the aluminum plate is the same temperature as the room temperature to start with. So we have to define the room temperature, which is the air temperature in the room. That would be 20 degrees. And for aluminum, we can look up some constants, for instance, the conductivity coefficient, which is 205 watts per meter per Kelvin. The density, rho, is 2,700 kilograms per cubic meter. And the heat capacity of aluminum is 900 joules per kilogram per Kelvin. If we look at the governing equation here, remember that we divide over with rho times Cp. So we will have something called K divided by rho times Cp. And this term, we can call it alpha. And that is the heat diffusivity. So we just define it directly here. Good. So that alpha is equivalent to the diffusion coefficient if we had a mass diffusion problem instead of a heat conduction problem. We call it the thermal diffusivity. Good. Okay, so now we should set the initial conditions of the plate. And because we have two dimensions, like before, we use the NP zeros to make the initial conditions. So we can just call it T here, T0 actually. And we need to first find out how long is the sides, the X grid and the Y grid. We define these with the length function. Like this. And the dimensions of the initial condition is then nx point ny. So we take a look at it. So now we are given a 2D array with a lot of zeros. So right now the temperature is 0 everywhere in the plate. Okay, but we want it to start at the room temperature. So we change all the internal and external points to the air temperature. We do it like this. So now everything should be 20, and it is. And now we have to set the initial conditions. And because we have Dirichlet boundary conditions, we can actually just set the edges being equal to 100 degrees. So we do this by using indexing. So all rows and column 0 should be 100. All rows and the last column should be 100. The first row and all columns should be 100. And the last row and all columns is 100. Whoops, it's T0 here. Let's have a look at the T0 again to make sure everything is as we wanted. Now we have an array with 100 in the edges and 20 inside. Good. Now we can, because it's a 2D array right now, we need to make it flat because we solved IVP cannot handle 2D arrays, so we need to flatten it using this function or method called flatten. And by typing in order equals false, we tell it to flatten it so it stacks all the columns on top of each other. Let's take a look at T flat. So now it is a 1D array. And of course, the first column is the edge that is out here. So all the first numbers will be 100. And then in the next column will come after here. So that will start with 100 and then 20, 20, 20, 100 in the end, and so on. Good. Now we are ready to define how the derivatives are calculated during each time step. And this is the range function. And the first thing we will do in our range functions is that the solve IVP will pass this flat 1D array into rates. And because we don't want to work with a 1D array when we actually have a 2D problem, we will convert, we will make the state variables as a 2D array from the flat array. We can do this with the reshape function. And the shape of the 2D array should, of course, be the dimensions, the length of the x dimension and the y dimension. And again, we have to use the argument order equals to false to do that. Then we need to define the derivatives, and we will just start by making the derivatives also as a 2D array. We can do that by saying it has to be the exact same shape as the state variables. We do it with the zeros like function. Okay. Now we are ready to make the interior points. Or maybe first we should just be explicit about the boundary conditions. Okay, so because we had a Dirichlet boundary conditions and we have 100 degrees on all the edges, we want to say that at the edges the temperature doesn't change over time because we always want 100 degrees here. So exactly like we did up here, we will set the change in temperature at all these positions to 0. And remember, it's the change in temperature, it's not the temperature itself we set here. And we don't want it to change from the 100 degrees at the edges. So the change is 0. Now we have actually handled all the 4 boundary conditions just using this code here. And that makes it also very explicit that we are handling the boundaries as Dirichlet boundary conditions. Now we will go to the interior nodes. So all the ODEs that describe how temperature change inside the plate, not on the edges. We have to model those now. We will do this by making a nested for loop. So that means that we have a for loop within a for loop. And why do we have to do this? Well, you have to think of it like that you have different, let's see if we can make some dots here. You have all the points inside the array here, and we are going to calculate them one at a time, and we will do this by first going through each row. So in the outer for loop, we will have the row indexing, and then within that for loop, we will go through each column in the first row. Then we will go to the next row in the outer loop, and in the inner loop, we go through each column in the next row and calculate the change over time. So we will call the first indexing along the rows for I, and it should go from index 1 to the last index exclusive. And we do that by typing in this. Now we have to define the inner loop, and we will call the loop variable for j in this case. And that will also go from 1 but to ny minus 1, because we're going along the other dimension now, nx and ny. And as you see, we are starting at position index 1 and ending 1 before the last, and that is because we already handled position 0 and the last point with the boundary conditions out here. So this is only the interior points we're going to loop through now. The governing equation looks like this. So we have a conductivity in the x direction and conductivity in the y direction. And we will split these terms up in two different lines. Okay, so just to go over it again, for the I index, we are looping over the columns in the x direction. If we have to stick with this figure, x is along the columns and y is along the rows. So in the inner loop, we are then looping along the ropes with the j index. And x, that would be corresponding to that we discretize over the x dimension, and therefore we have to change y. So the central difference would be like this: I minus 1, and here we have a fixed j minus 2 times I j plus t I plus 1. Good. And then we also have to write the conductivity in the y dimension, and here we fix I and vary j instead. And we have to divide by dy here instead. That's all good, so we can write the governing equation down here. And here we have to remember that we multiply by alpha times these two terms. So what we have here is the description of the pure conductivity in the plate. But we must not forget that we also have some heat loss from the surface of the plate. And we have to therefore calculate the exact loss of heat from each cell, because we are looping through each cell here. So we also have to talk in terms of cells down here, or nodes, whatever you want to call it here. So we can calculate some of this outside. So first we have to calculate the mass of a cell. So the mass of a cell would be dx times dy times the depth. This is where the depth enters, times the density. So this is the mass of the cell, and that is important because the whole cell is giving away energy, and we need to calculate this correctly to get the correct loss of heat. And it's only losing this energy through the surface of the cell, and that is just dx times dy. Oops. So we can write the energy loss. That is a function of, that is actually the same as Newton's law of cooling. We have some heat transfer coefficient, and we have the temperature difference between the cell and the surroundings, which is the air. And then because it's big Q here, we have to multiply by the surface area. If we had a small q, it would be per square meter. But here we make it very specific because we're in the loop where we only look at one cell at a time. We have to multiply by the surface area of the cell. So this would be the energy loss. But remember, in our governing equation, the energy loss would be the S term, and we divide that by rho times Cp to get the conversion to temperature. So down here we can subtract the Q loss, and we divide by the mass of the cell times Cp, like this. If we did not use mass of the cell and we just used rho up here, it would again be in units of per cubic meter, but we want it specifically for the size of the cells at each node. Therefore we use the mass of the cell here to correct for that. Alright. So now we have written the whole for loop for the interior loops, and we can now return the derivatives. But we are not quite ready yet, because right now, as it is in the code, we are having a 2D array. Remember, we made it a 2D array up here, and solve IVD needs a 1D array. So we have to flatten it again before we send it back to solve IVP. So we use the flatten function and use the argument order. The argument order equals f before we return it. And we can actually just put it directly down here in what we return, like this. We are now done with the range functions, except that we need all the arguments inside it. So let's go up and type all the arguments in. So we need time, the temperature state variable in a flat version, h, the heat transfer coefficient, alpha, gr, dx, dy, depth, nx, and y. That should be it. And these arguments we also need in our solve IVP. Just have them here. So the solution, solve IVP, we will call the rates function, our t-span. Let's go for from 0 to tmax, and we can put tmax to 500 seconds. Then we need the initial conditions, which will be T0 flat, and we then need the method. We'll use the BDF method here. T eval will be equal to the lens space and width 100 points. And then we will pass the arguments and we will just copy from up here. Okay, let's just try to run this and see if that works. Um, oh, we have to define H. So that is the heat transfer coefficient, and we can look up in some tables what value to use, but we'll go for a value of 5 in this problem. And let's try to run everything. And we then have the solution, and I will take some pre-written code for the animation and try to plot that. So we see the heat spreading into the middle over time. And we can try to plot the temperature in the center, and we are after 60 degrees here. So that only takes around 30 to 40 seconds before we reach that temperature in the middle. If you don't get this animation to work, it could be because you have to activate a setting in here in preferences. You have to go into preferences and go to IPython console, graphics, and then you have to here in the back end, you have to select automatic, and I think by default it is inline that is chosen here. And then click apply and rerun it, and then the animation should appear in a separate window down here you can open.